In this video, I'm going to look at the sign test, which is a non-parametric alternative to a one-sample t-test or a paired t-test. The data we're going to look at concerns a study that was done into insects, and the theory that was being assessed is whether insects where the female mates multiple times leads over time to an increased number of species relative to a similar insect group where the females mate only once. And so the data here is the study design was set up in such a way that we've got paired insect groups. So we've got a multiple mating group and a single mating group, and we've counted the number of species in each group, and then we've taken the difference between those two numbers. And so if we look at a histogram of those differences, we can see that we've immediately got an issue if we want to try and apply a one-sample t-test to this data, because the one-sample t-test relies on a normality assumption, and we've clearly got data that did not come from a normal distribution here. Over here is where most of the data is on the left, but then we've got this one outlier here that sticks out like a sore thumb. So if we were to go ahead and try and use a one-sample t-test on this data, any results we would get would be totally worthless, because that normality assumption that we rely on to do the test, unless we've got a huge sample size, which we don't in this case, we've only got a sample size of 25. So if we were to use that one sample t-test here, we're not going to get results that we can use. So we need to remedy this problem somehow. In the last video, we had this problem crop up, and we were able to transform the data in such a way that the normality assumption for the transformed data seemed reasonable, and then we could use our statistical analysis on the transformed data and then back transform the results into our original measurement units. That approach would not work in this case, because this data is so extreme, this outlier is so much larger than all the other values. It doesn't matter what transformation we use here, we're not going to be able to get data that satisfies the normality assumption. So we need a different approach. And so the approach we're going to take in this video is to use something called a non-parametric analysis. And non-parametric analyses are methods that we can use when the test that we're trying to do relies on an assumption that does not seem to be supported by the data. And so specifically in this case, we want to do a one-sample t-test. That requires a normality assumption to be satisfied. The sample data don't appear to support a normality assumption, and so that's where a non-parametric alternative comes into play. You might ask yourself, well, why don't I just use a non-parametric alternative all the time? The reason is because non-parametric tests tend to be less powerful than the parametric tests. And so ideally, if the data do satisfy the underlying assumptions, a parametric test will perform better than a non-parametric alternative. But if you are unable to satisfy the assumptions with your sample data, then you cannot use a parametric test, and you will have to use the non-parametric alternative, unless you're able to take the approach we did in the last video and apply a transformation, and the transformed data does satisfy the assumptions. Okay, so let's go on and do this. So the way this particular non-parametric test works is as follows. So this is the sign test, and here's our data that we need to work with. And so this is the differences in the number of species between the multiple mating group and the single mating group for each insect taxa. And what we want to do is we want to look at each number and figure out if it's greater than 0, less than 0, or exactly equal to 0, and keep a tally of each of those categories. So we could do that by hand in this case. It's not too big a deal, or we could just use this piece of code here, and we end up with this table. So there were 7 negative differences, 18 positive differences, and there were 0 differences. Okay, the next step is to add up the number of negative differences and positive differences. If we did have any 0 differences, we would actually discard those, and those don't become part of the analysis. So n is the sum of 7 plus 18, and then this test works like a binomial test. So we covered the binomial test in one of the earlier lessons, and so what we're doing now is we're just applying a binomial test to this table, essentially, ignoring the category in the middle. So we've just got 2 categories, negative differences and positive differences, and so just running through the binomial test again, we set p equal to 0.5. We create a vector of a number of successes going from 0 up to the sample size, and then calculate the probabilities for each of those numbers of successes, and then our test statistic is the larger of these 2 numbers, so it's 18 in this case. So let me just back up for a second. I'm doing a hypothesis test. I need to be careful to go through my 4 steps. So I kind of skipped over step 1. Step 1 for a sign test is that the median difference in the number of species between the insect groups is 0. So the sign test isn't focused on the population mean, it's focused on the population median. Okay, so that's one thing you need to be a little careful of here. Okay, so that was the null. The alternative hypothesis is that the median difference in the number of species between the 2 groups is not 0. Okay, that's step 1. Step 2, test statistic. Okay, there's the test statistic there, x. 18 in this case. It's the larger of these 2 numbers. Next step is calculate the p-value. So the p-value is, we've got these probabilities, and we're going to add up the probabilities for number of successes greater than or equal to our test statistic, and then we'll multiply that by 2 to get our p-value. So there's our p-value. And step 4 is make a decision, draw a conclusion. Decision rule, reject the null in favor of the alternative if the p-value is less than the significance level. So we ask ourselves, is 0.043 less than 0.05? Yes, it is. So we reject the null in favor of the alternative. And so it does, the data do appear to support a median difference in number of species between the 2 insect groups as not 0. We can skip all this hand calculation if we just use this binom.test function, and that gives us all the results right away. So there's the test statistic, there's the p-value, and so we can conduct our test a little bit quicker if we just use this data here. So that's the sign test. Very straightforward. It's pretty much just the binomial test applied to this table here. ignoring the equality category